Okay, so here I will do an example of QR factorization using the Givens rotation, using Givens rotations. So let's say that I have the following matrix. Okay. So first I will try to eliminate this element here. Okay. Because remember we want to get an upper triangle matrix. Okay, and so the elements below the diagonal should be 0. Okay. And so our first Givens rotation, let's call it J1, will be equal to the negative sign is where the element is that we want to eliminate. The two cosines are on the diagonal, and the two cosines, the negative sign and the sign, they have to form a square. Okay. And so in the third dimensions there will be a 1 in the diagonal and 0 elsewhere. And so our cosine will be the top element of the first vector, so 1. Okay. Over the square root of it will be so we have 1 squared plus the element we want to eliminate squared, so 4. So we will get 1 over square root of 5. And our sign will be the element you want to eliminate, so 2 over the square root of that element squared, so 4, plus the top element, so 1. So we will also get 1 squared, sorry. So we will also get 2 over square root of 5. Okay. And so if we apply our first rotation to A, we get 1 over square root of 5, negative 2 over square root of 5, 2 over square root of 5, 1 over square root of 5, 0, 0, 1, 0, 0, times our matrix A, so 1, 2, 2, 2, 2, 1, and 2, 1, 2. Okay? And so we should get 5 over square root of 5, 0, and 2. Then we will get 6 over square root of 5, negative 2 over square root of 5, 1, and then 4 over square root of 5, negative 3 over square root of 5, and 2. Okay, now we want to, first let's call that A1, okay. We want to eliminate this element here, so our Givens rotation J2 will be given by the negative sign will be here. The true cosines need to be on the diagonal, and the two cosines, the negative sign and the sign, they need to form a square, okay? And so our cosine will be given by the top element squared. So I just see that we can rewrite 5 over square root of 5 as square root of 5. Okay, if we multiply by square root of 5. Okay, so if we multiply, we will get square root of 5. So that makes things a bit easier. So we will get the top element, so square root of 5 over the square root of that element squared, so 5 plus the element you want to eliminate squared, so 2 squared, so 4. Okay, so it will be square root of 5 over square root of 9. And our sign will be, it will be the element we want to eliminate over the square root of that element squared and the top element squared, so 5, so we'll get 2 over square root of 9. And so now if we apply our given rotation to our matrix A1, we will get the following. By the way, instead of square root of 9, I could just write 3. It would be easier, maybe. Okay. And our matrix A1, so square root of 5. Okay, because remember we multiplied by square root of 5 on the top and the bottom of 5 over square root of 5. Okay, 0 and 2, 6 over square root of 5. 1, 4 over square root of 5, negative 3 over square root of 5, and 2. Okay. And so if we multiply that, we should get 9 over 3, okay, or just 3, 0, and here we should get 0, 2, okay, so you get negative 2/3 times square root of 5 plus 2 times square root of 5 over 3, okay, so you get 0. Then here you will get, so here we will get 8 over 3, negative 2 over square root of 5, and here we will get negative 7 over 3 square root of 5, and so here we will get the following. Okay, now we want to eliminate this element here of the second column vector, and we will also consider this 2 by 2 submatrix. Okay, remember, because we don't want the second element of the second vector to also become 0, okay, because we want an upper triangular matrix. Okay, so we only want the last element of the second vector to be 0. Okay, and so if you only consider this 2 by 2 submatrix, or third given rotation, let's call it J3 prime, because it will be 2 by 2. It will be given by negative sine, cosine, cosine, and sine. Okay, and the cosine will be the top element of the vector in the submatrix, so it will be negative 2 over square root of 5, okay, top element in the submatrix, so it will be that, so it will be negative 2 over square root of 5 over the square root of that element squared, so 4 over 5, plus the element you want to eliminate, so negative 7 over 3 times square root of 5. So this will be 49 over 9 times 5, which is 45, I think. I hope I did no mistake. I think it's good. And so we can rearrange that a bit. We can multiply by 9. Here we can multiply by 9 over 9. And so we get 38, or 46. Wait. Yeah, 36 plus 49, so 79, so 85 over 45. Okay, I think this should be correct. So we can rearrange that again. If we divide by 5, so here if we divide by 5, we get 20, no, we get 17 over 9. Okay. And we can rearrange that again. We get, if we take the square root of 5 inside, we get square root of 85 over 9. Then we can distribute the square root. And now we can take the square root of 9 on the top, get negative 6 over square root of 85. Okay, I hope I did no mistake. Okay, so that should be our cosine. And our sine should be the element we want to eliminate. Over the square root of that element squared, so 49 over 45 plus the top element squared, so 4 over 5. Okay, and so we can rearrange that again. We get negative 7 over 3 times square root of 5 times times 1 over square root of 17 over 9. Okay, because these are the same values as here, basically. And so we can find this here. And now we can distribute the square root here and take the 9 on the top. So we get negative 21 over 3 times square root of, we can multiply 5 and 17, we get 85, I think. And so we can divide by 3, we get negative 7 over square root of 85. I think this should be correct. Hope I did no mistake. And so that's our Givens rotation if you only consider the 2 by 2 submatrix. Now if we want to multiply by A, we need to have the same number of columns as A has rows. So A has 3 rows, so we need 3 columns. And so basically we will define our Givens rotation J3 to be equal to 1 and zeros in the same row and column. And here we will put our Givens rotation J3 prime. Okay, and so J3 prime will be this value here, negative 6 over square root of 85. Okay, so our J3 will be the following. Okay, so we can multiply our matrix A with this matrix J3. So we get sorry, our matrix A, it's not 8 that you are multiplying, this is A2, so the result of our second rotation, so this is A2. Okay, and here we have I think this should be correct. Okay. Okay. And so if we multiply that out, we should get 3, 0, 0. Here there should be no change. 8 over 3 and 8 over 3. Okay, this shouldn't change. Now here we have negative 12 over square root of 85 times 5. So I think we can let it so. You can multiply it if you want, but you can just write square root of 5 times square root of 85. And there should be a plus here. I think. Yeah, there should be a plus. Then 49 over 3 square root of 5 square root of 85. Okay, then this mistake. We have to add these two terms. So this will become a bit messy. Okay, here we get negative 14 over square root of 5 square root of 85 plus yeah, that should be correct. It's just a little bit messy, but otherwise it's fine. Okay. And so here we should get 18 over square root of 5 times square root of 85 plus 14 times 3 square root of 5 square root of 85. And here we should get negative 21 over square root of 5 times square root of 85. Okay. Plus 12 over 3 square root of 5 square root of 85. Okay, I hope you can still see it. Okay, so this should be correct. I hope I did no mistake. Now, here, if you multiply by 3 over 3, you get the same denominator. We get negative 42 plus 42 over 3 times square root of 5 times square root of 85. And so we just get 0. Okay. So all this here becomes 0. Okay? And that's what we wanted at the beginning, okay? but I just wanted to do the computation first, so to see the values I get. Okay. I think I can also find the same denominator by each element. We'll just try to clean that a bit. Here, if I multiply by 3 over 3 by the first element, I get 36 plus 49. 36 plus 49, which is 85, I think. 85 over 3, sorry, square root of 5, square root of 85, 0. Then here I would get 54 plus 14, 54 plus 14, which is 68 over 3 times square root of 5 times square root of 85. Then at the bottom, so here I should get negative 63, negative 63 plus 12, so negative 51, I think. Negative 51 over 3 times square root of 5 times square root of 85. I think this is correct, and here I have 8 over 3, 8 over 3, okay. And so that is your upper triangle matrix, okay, if everything is correct, okay. And so your matrix Q will be equal to J3, J2, J1 transpose. So this will be J1 transpose, J2 transpose, J3 transpose. Okay. And so yeah, you can write your matrix. I won't calculate Q here because otherwise we need some time. And now I'm not even sure that I did no mistakes. So yeah, but you can do the computation. You just need to to find the product of J3 transpose. So this matrix here, transpose of course, J2 transpose, so this matrix here, and J1 transpose, okay. Yeah, and so you can get your matrix Q. And so here we got our matrix R, okay. So yeah, you just need to find the given rotations, okay. To find the structure of the given rotation, so where do you put the cosines, the sine, and the negative sign in the matrix? Once you are finished with the first vector, only consider the submatrix of the second column vector, for the second column vector, okay? Don't forget to only consider the submatrix, otherwise you also eliminate the second element of the second column vector, but you want an upper triangle matrix, okay? You don't want the second element of the second column vector to also be 0. And yeah, so yeah, you apply your rotations to your matrix A, and then you find your upper triangle matrix, and then you can find the matrix Q by finding the transpose of the product of the given rotations. And yeah, Thanks for watching.